Welcome to this topic of the Demystifying IPv6 course on IPv6 Addressing. IPv6 Addressing is actually broken out into two parts, so there will be two separate topics, and this is part one. So as you can see from this slide, comparing the IPv4 address space, which uses 32 binary bits, to the IPv6 address space, which uses 128 binary bits, there is a big difference in the number of available addresses. 4.29 billion with IPv4, 3.4 times 10 to the 38th, which is a large number of addresses. In fact, 340 undecillion addresses, where undecillion is actually a billion. There's all kinds of statistics that you find regarding the size of the IPv6 address space, such as there should be enough IPv6 addresses to label every grain of sand on the earth. Another one that's mentioned on this slide is there's 665 sextillion addresses per meter squared of the Earth's surface. Just to get an idea of how big a sextillion is, as you can see, it's a 1 followed by 21 zeros, which translates to 1 billion trillion. Well, how is the IPv6 address space represented to us? Of course, binary bits are always stored within the computer's memory, but we tend to simplify it for us human beings. So when we write things down or see things read out on a computer screen, like let's say if you're looking at a route table or something like that, it makes more sense. So in order to represent that, first the 128 bits are divided up into 8 double octet fields, or blocks of 16 bits each. The way this is written and displayed to us is documented in RFC 4291, the IPv6 architecture. Each 16-bit block that's represented on the previous slide is converted to hexadecimal and delimited with colons. So the resulting representation is called colon hexadecimal. So even though what you see below still looks a little bit unwieldy to us human beings, it's definitely better than looking at 128 binary ones and zeros. This slide depicts an example collection of IPv6 addresses just to get you used to what you might be seeing out there in the real world. Actually, the first address is not an IPv6 address, it's actually an Ethernet MAC address. It's a multicast MAC prefix 33:33 that's used when mapping down IPv6 multicast addresses down to an Ethernet multicast MAC address. More about that on a subsequent slide. The second items are what's referred to as IPv4 compatible addresses. So it's a way to embed IPv4 addresses into the IPv6 address space with really no other IPv6 prefix information. In fact, all of those have been deprecated or are no longer in use today. There's a lot of other addresses types that are listed on this specific screen. Addresses such as FC01, 2001, 3FFE, FE80, 2002, FF02. We'll learn more about what those actual prefixes represent, but they do represent some specific type of IP address in the IPv6 address space. And some of the last items on this slide, 0200:/3 is what's referred to the aggregatable global IPv6 space, really the public IPs that are in use today, and then a couple of other special addresses, ::1::, that we'll discuss on some future slides too. So the next step in making the IPv6 addresses a little bit easier to work with and view for us human beings is a concept of being able to remove or compress zero spaces in the 16 blocks that I mentioned before. So as you can see, leading zeros can be omitted. A block of all zeros can be represented with a : So as you can see, the top address that starts with 21DA has got reduced in size. Instead of 00D3, it's just D3. Instead of 4 zeros, we can represent that with just 1 0. The 0 before the 2AA has been omitted as well. The 2 zeros before FF have been omitted as well. Also, successive 16 blocks of zeros may be simplified or compressed using a double colon. So a long string of bytes that have all zeros, in this case FF02 colon 0 colon 0 colon 0 colon 0 colon 0 colon 0 colon 2, it can actually be represented as FF02 colon colon 2. May not be obvious, but there are certain limitations to removing and compressing zeros because it becomes ambiguous as to what they actually started out to be. So trailing zeros within a 16 block cannot be removed. Also, the idea of compressing multiple 16 blocks of zeros using the colon colon can only be performed once, and you'll see why on the next slide. The reason the double colon can only be used once is the way that you can reverse engineer just how many zeros were actually compressed. So if you look at the result, how many of the 8 16 blocks are left, subtract that many and then multiply that by 16, and then you get the exact number of zeros that were actually compressed. Obviously, if this was done more than once, there would be no way to figure this out. So IPv6 prefixes, and over the course of the history of the internet and IP addressing in general, a prefix was used to indicate the routable portion of the address from your point in the network hierarchy. So as per CIDR, different points like the core of the internet will use shorter prefixes. Your organization will use prefixes plus subnets, and then there even may be like host-specific routes. And so an IPv6 prefix is represented as an IPv6 address / the length. And that's, again, came from the CIDR or classless interdomain routing scheme. So as you can see here, if we have an example prefix of the hex 12AB followed by some zeros, CD3, and we wanted to indicate that it was a 60-bit prefix, there's different ways of representing it. For instance, in the first example, remember the trailing zeros cannot be omitted. In fact, that's the whole prefix completely written out. In the second example, double colons have been inserted to represent the two 16-bit blocks of 0, but of course that could only be used once. And then because all the trailing bits in this prefix are 0, in other words the interface portion, which we'll talk more about later, is just represented by zeros, then we can use the double colon to compress the end of the address instead of the beginning because there's more zeros that are actually being compressed. So in certain cases it's beneficial to write the entire node address and indicate its prefix to, so you can combine the two concepts where if the entire node address is as depicted in the first example below and its subnet was as depicted in the previous example with the 60-bit prefix, then the entire address can be written out /60. Keeping in mind that with IPv6 there was never a concept of dotted decimal subnet mask. So here's a few IPv6 prefix examples, because in the previous slide I mentioned it's the routable portion, or it depends on your place in the network as to which bits are actually significant to you at the time. So if you're in the core of the network, for instance, you'll generally use a /48, which is an entire route prefix. Within the organization, you'll use the following 16 bits after the 48 as your subnet prefix, and then you'll be working with a /64. Of course, if you want to indicate the entire host address, then you'll use all 128 bits. So you'll use a /128 prefix. So IPv6 actually has an implied network prefix. So in other words, the most significant 64 bits of the address are the network portion, and the least significant 64 bits of the address are the interface ID. And that's always the case now with the address space that we're working with for IPv6. So there are different IPv6 address types. There's Unicast, Multicast, and Unicast. Also, keeping in mind that broadcast has been eliminated in IPv6. And so we'll talk more about how that's accomplished, especially when we get into the neighbor discovery portion of IPv6, because that's generally, for instance, where IPv4 used broadcasts to discover neighbors using ARP. So in the Unicast space, there are special addresses, which we'll talk about in some subsequent slides. Scoped addresses, in other words, is this meant just for this link or just within your organization or internet-wide? Also the global IPv6 address space, in other words the routable portion on the IPv6 internet, they're also referred to as aggregatable global unicast addresses. There are various different types of multicast addresses, including a special address called the solicited node address, which we'll talk about more later. Also Unicast. So Unicast, I wouldn't say it's a new type of address because it's been around since the early days of IPv4. So the concept with Unicast is that you're looking for the nearest device or router to you. And finally, an interesting concept with IPv6 is you assign the addresses to interfaces and not necessarily the entire node. So whereas with IPv4, a single node may only have one address, with IPv6, a single node, not only that, a single interface might even have multiple addresses. In fact, it does for special cases. So looking now at some IPv6 unicast address types. So I mentioned on the previous slide the aggregatable global unicast address space. All addresses starting with 001, which translates to a hex 2, comes out of that space. Link local addresses always start with FE80/10. Unique local addresses, which we'll talk more about, somewhat analogous to IPv4's private IP address spaces, in other words just used within your local organization, have prefixes such as FC00/8, FD00/8, and then the multicast address space starts with FF00/16. So over the years, as we've been rolling out IPv6 address space, there was an RFC 2450 that was written that worked out of the same aggregatable global unicast address space with the format prefix set to 001, which of course would imply that the first nibble was a 2, although it could possibly be a 3, but via RFC 2540 it was actually set to just 001, and it specified the next level identifier called a TLA ID, followed by a sub-TLA ID and an NLA ID. TLA meaning top level aggregator, NLA meaning next level aggregator, and RFC 2450 actually set the format prefix in the TLA ID to 2001 hex. So the idea then was providers would use a sub-TLA and then organizations would use the NLA to number their address spaces into subnets. So this was interim rules. It was used for a while. It's no longer used, although there still are a lot of interfaces out there that use a 2001 prefix, and so you'll see that quite commonly in a routing table. Instead, RFC 3587 came up with a new strategy for structuring the aggregatable unicast global prefix space. So again, we're still working out of the same block, 001 prefix, but now there's a global routing prefix and an SLA, so we've relaxed some of the very specific TLA, sub-TLA, NLA restrictions that were described in the previous scheme, and now we're just looking at a global routing prefix, which is a /48, and those will be the prefixes that will be given out to organizations. So an organization will get a /48, and then that site that within that organization can use the next 16 bits for their site level aggregator, in other words the subnets within their sites. Keeping in mind that IPv6 does have an implied address structure where the most significant 64 bits are the network side and the least significant are the host. So we're still operating under those restrictions, as well as the first 3 bits being 001. But now the routable portion of the address is broken up into a /48 and then a /64 for organizations. One interesting concept relative to the least significant 64 bits of an IPv6 address is the interface ID. In fact, how that interface ID is actually derived. So from RFC 4291, you actually use the Ethernet or MAC address, or what's referred to as the EUI 48 address, and embed it into the interface ID of the device. And so in doing so, you create what's referred to as an EUI64 formatted address, which is 64 instead of 48 bits, and of course 64 bits fits into the interface ID portion of the IPv6 address. So in order to derive an EUI64 from an EUI48, you start with the original MAC address, slice it open in the middle, insert the value FFFE, take the most significant byte, which I'll discuss more about that on the next slide in case you're not familiar with what I call the anatomy of a MAC address, but the most significant byte, the two least significant bits, in fact a second least significant bit is the U bit, where it's either unique or global, and we'll talk more about that on the next slide. But when you convert an EUI48 address to an EUI64, you actually invert that bit. And so whereas the MAC address might have started with 00, the EUI64 address will actually start with 02. So this slide depicts the EUI48 or MAC address, and as you probably know, the most significant 3 bytes are the vendor ID. So in other words, the IEEE, if you pay them $1,200 or so, you can get your own unique ID, and then you can use the least significant 24 bits that has 16 million combinations available, 2 to the 24th, and assign a different value to each interface that you produce. Well, in the most significant byte, there are the 2 least significant bits. The very least significant bit is the IG bit, the individual or group bit. And that bit is set or unset depending if it's for one or more addresses. So if it's just for one address, it's always 0. But if it's for multiple address, i.e. a broadcast or a multicast address, then that bit will be set. So the least significant bit or the most significant byte would be indicating that it's for multiple devices and not just one. Well, the second least significant is the UL bit, universal or local, meaning is this a burnt-in address? Is it universal and not duplicated anywhere in the world? Or is it configured through software, meaning that it's locally administered? Keeping in mind that this second least significant bit of the most significant byte is actually the bit that gets flipped when you map down an EUI48 address to an EUI64 address, as discussed on the previous slide. So we've talked about the different types of addresses. How are they assigned to hosts, which are talked about on this slide, and to routers, which are talked about on the next. So what type of addresses does an IPv6 host have? Well, an IPv6 host has unicast addresses. There's a special type of address now that's called a link local address that it will assign automatically to each of its interfaces, and we'll talk more about that in part 2 of this series on IPv6 addressing. There's possibly other unicast and even unicast addresses that could be assigned to one or more interfaces on the device. And there's also the loopback address, which you're probably familiar with IPv4, the 127.0.0.1, whereas with IPv6 it's just all zeros ending in 1 or colon 1. There's also some multicast addresses. So previously I mentioned how IPv6 does not use broadcast anymore. So that uses a special scheme with various types of multicast addresses to accomplish the same thing that broadcasts accomplished with IPv4. So there are special multicast groups, the node local, all nodes, or link local all nodes multicast addresses. There's a solicited node multicast address, and various other types of multicast addresses of joined groups. An IPv6 router has similar but additional addresses as an IPv6 host. So from a unicast perspective, yes, it does have link local addresses for each interfaces, unicast addresses for each interface, the loopback address. It has a special anycast address, which means any router on this subnet, and then various different types of multicast addresses. The same all nodes addresses, but also all routers addresses for both node local and link local. There's also the solicited node address and various multicast addresses that the router might be joining. If it's a router, for instance, if it's running OSPF for IPv6, which is OSPF v3, there's a special multicast address for the all SPF routers in the IPv6 world, just as there was in the IPv4 world too. Thank you for taking the time for viewing this topic of the Demystifying IPv6 course on IPv6 Addressing Part 1. Welcome to this topic of the Demystifying IPv6 course on IPv6 Addressing. This topic is actually the second part of a two-part series on the IPv6 addressing. The Internet Assigned Numbers Authority, or IANA, is responsible for the global coordination of the DNS route, IP addressing, and other Internet Protocol resources. Specifically, the IANA allocates and maintains unique codes and numbering systems that are used in the technical standards or protocols that drive the Internet. IANA's various activities can be broadly grouped into three categories: assigning domain names, protocol assignments, and number resources. For the number resources specifically, the IANA coordinates the global pool of IP and AS, or Autonomous System numbers, providing them to Regional Internet Registries, or RIRs. Both IPv4 and IPv6 addresses are generally assigned in a hierarchical manner. Users are assigned IP addresses by Internet Service Providers, or ISPs, and ISPs obtain allocations of IP addresses from local Internet registries, or national Internet registries, or from their appropriate regional Internet registry. The AFRINIC, or African Network Information Center, covers the African region. The APNIC, or Asia Pacific Network Information Center, covers the Asia Pacific region. ARIN, or the American Registry for Internet Numbers, covers the North American region. LACNIC, or the Latin America and Caribbean Network Information Center, covers Latin America and some Caribbean islands. And finally, RIPE NCC, or the Réseau IP Européens, or French for European IP Networks, covers Europe and the Middle East and Central Asia. This slide depicts the IPv4 exhaustion counter as of March 26, 2011. At the bottom of the screen, you can see that there is a link that you can access to view this exhaustion counter yourself. One thing you'll notice is as of February 3, 2011, the IANA has exhausted all the available blocks. In other words, it's allocated everything it has to the regional information registries. And as you can see, the regional information registries are depleting their resources as well. So the IPv6 address space is 128 binary bits. And as you can see, there is a block called the Global Unicast block, which starts with 001, which in fact is 1/8 of the total address block available, is what we're currently using to allocate global unique IPv6 addresses today, as per RFC 3587. There are a few other blocks, smaller portions of the address space, which have been allocated for things like unique local addresses, link local, and the multicast address space. Obviously, there are many blocks, many available IPv6 addresses that are not even being currently allocated today, and who knows if and when they ever will be. So, some of the special addresses that I'll talk about here, starting with the link local address space. And as you can see, I've depicted it in a number of ways at the top of the screen. It's out of the block that starts with FE80::/10. Or you can say the link local unicast address starts with an FE80::/64 prefix. In other words, the remaining 48 bits are all zeros. And you could also say the prefix FE80::/ is followed by the device's interface ID. So the idea with link local is to scope the packets that are sent to or from it with only a span of the local link. It's an address that's automatically configured on all nodes. It's used for special processes, as we'll discuss in another topic in this course, for neighbor discovery and router discovery. It may also be used for non-globally routed IPv6 local network. So in other words, two devices on the same link may use these addresses to communicate with each other. And finally, it's used when we want to make sure that packets are not forwarded any farther than the local link. So if routers see this, they'll just drop the packets, unless it's destined for them. Originally, there was a site local unicast address, which has since been deprecated. The idea was to create an address similar to the private IP addresses in IPv4. But since it's been deprecated, I won't discuss it here. Rather, let's move on to the next type of address. So the unique local address, or the address base starting with FC00::7, is actually what's used in place of the site local address today. The usage of this address block is defined in RFC 4193, and they're used for systems that are not connected to the global internet, but rather routable within your own enterprise. There's actually two variations, depending on if the least significant bit is set or not. It could be FC00::8 or FD00::8 if the bit is set, as to how that address base is managed. If your global ID, in other words the 40 bits following the FC00 space, is managed by the IANA, in other words that prefix is given out, and then the least significant 16 bits of the network half of the IPv6 address can be used by the organization to manage their subnets. FD00 uses a randomly generated global ID instead. A couple more special addresses. There's the unspecified address, or just : which, as I discussed in the intro topic to this series, is just all zeros. It's used when you have no address available to use, so generally you'll see it with your DHCP requests or with duplicate address detection, or DAD. There's also the special address for loopback, which is : which basically identifies yourself. It's like 127.0.0.1 with IPv4. So for instance, if you want to ping yourself, you'll use not ping, but ping6 space : to send a ping request to yourself. How about multicast use? Well, with IPv4, a lot of functions were performed using broadcasts. As we know, broadcast interrupts all the computers on the LAN, and in fact can completely create a LAN useless in the case of a broadcast storm, i.e. too many broadcast packets on the wire. Broadcasts are not used in IPv6. I mentioned that in the part 1 of the IPv6 addressing, but there are certain multicast processes now that enables more efficient use of the network with IPv6 and replaces broadcasts instead. In fact, the multicast range of addresses, of course, like everything else with IPv6, is much larger. So how about the multicast address format? The address is divided up into 4 different fields. There's the format prefix, which is the FF starting at the beginning, or all ones for 8 bits, followed by the flags for 4 bits, scope for 4 bits, and then 112 bits of global ID. And so you can notice, depending on the scope or the ID bits, will depend on whether it's a node local or link local, if it's for all nodes or all routers. There's also even special multicast addresses for things like OSPF v3. So the format prefix, as I mentioned, a multicast address always starts with FF, or 8 binary digits. That's the address space which the multicast addresses are allocated out of. The multicast address flags, of which there are 4, are broken up into the T flag, which is the least significant bit, which determines whether it's a well-known address that's actually assigned by the IANA, if it's 0, or if it's 1, it indicates a non-permanently assigned address, generally one that maybe an organization is using for its multicast applications. There's also a P flag, which its definition and usage can be found in RFC 3306, and also an R flag, of which its definition and usage can be found in RFC 3956. The scope field indicates how deep that packet should penetrate into the network, whether it's of local scope to the host, it's of a link local scope, so it can go on the wire but no further, and so on. And so with IPv4, there was no way to tell within the multicast packet just what its actual scope was. You had to maybe compare that with the IP time to live that was set to see how deep that it was going to go into the network, whereas IPv6 embeds the scope directly into the multicast address itself. The multicast address group ID is the least significant 112 bits, although it's recommended to only use the least significant 32. And the reason that is because of how a multicast IPv6 address is mapped to a multicast MAC address. It only uses the least significant 32 bits. The multicast MAC address with IPv6 starts with 3333, followed by 32 bits, which are the least significant 32 bits of the IPv6 multicast group ID. There is a special type of multicast address called the Solicited Node Multicast Address, or SNM. And you can see it has a special prefix. Of course, since it's multicast, it starts with FF. It starts with FF02 because it's got a link local scope. And then it's followed by 104 bits, of which most of them are zeros, followed by a 1:FF. Plus, the least significant 24 bits are actually derived from the node's IPv6 address. And if you remember, the node's IPv6 address, specifically the least significant 64 bits, are derived from the EUI64 address, which is a derivative of the device's MAC address, the EUI48, with FFFE in the middle. And so as you can see, the least significant 24 bits, in general, is a derivative from the least significant 24 bits of the host's MAC address, which, of course, is not necessarily globally unique, but for any specific OUI value, it should be unique, or at least it has a 1 in 16 million chance of being unique. So essentially what you can do is you can configure a device, or through some automatic mechanisms, which I'll talk about later, a device can configure itself using its own MAC address, creating its own solicited node multicast address, which has a 1 in 16 million chance of being unique on any one subnet. I'll talk a little bit later as to why this is done, but the idea led to the notion that multicast can replace broadcasts in IPv6, because if I know an interface's IPv6 address, I can reverse engineer what its solicited node multicast would be. And therefore I can send out a packet on the wire without knowing its actual MAC address and have only that device, or a 1 in 16 million chance that only that device replies. So the usage I mentioned, in this example, we have two devices, device A and B. They want to communicate. Each one knows each other's IP address. The idea is, well, how do I know your IP address? Well, I probably figured out using DNS and so on. But if I know your IP address, but then I want to send a packet to you, but I don't necessarily know your MAC address, again, the MAC address could be embedded in the least significant 64 bits of its IP address, but I can't always assume that. But I can reverse engineer what your solicited node multicast address is. And then I can map that down to an actual MAC address that you're listening to, because your network interface card will listen to several different types of MAC addresses. One that are addressed to its burn-in MAC address, which again is something I don't necessarily know at this time. Broadcasts, which again we've eliminated with IPv6, or any multicast groups you have joined. And the solicited node multicast address is a group that you will join, so your network interface card will be listening to that. And so that way I can send you a solicitation and be assured that you, and maybe not only you, because there's a 1 in 60 million chance that another device will intercept that on the wire as well. But the good news is that maybe only one other device instead of every device, as was the case with broadcast and IPv4. As I mentioned in a previous topic, Unicast addresses are not necessarily unique to IPv6, but they were the first time that they were defined within the protocol standard. IPv4 had Unicast as a separate RFC that it described, and an Unicast concept comes from that same RFC as well. But the idea is that I have multiple different interfaces, multiple different devices, or something that has the same addresses, and I'm looking for the one that's nearest to me. So the nearest concept comes from the fact that we advertise an Unicast address as a host route, so in other words a /128 in IPv6, and then the routers will determine, even though they have multiple sources of that same address, which one from where you're oriented the network is the closest. So possible uses of Unicast addressing is to force routing through a specific ISP, to find the nearest home agent for mobile IP services. So as you travel from cell site to cell site, for instance, you want to find the nearest home agent, but using a well-known address, or an Unicast address, of course. For DNS services, looking for the closest DNS server to you, and for redundant application servers. This slide I'm going to build out on the right-hand side to map the corresponding IPv6 address to the existing IPv4 address type. So starting with the top item, global unique IP addresses in IPv4 are referred to global unicast addresses in IPv6, whereas IPv6, they're virtually unlimited. Multicast addresses that started with 224.0.0.0/4 with IPv4 are FF00::/8 with IPv6. Broadcast addresses are eliminated with IPv6. The unspecified address, or all zeros, is depicted as just : with IPv6. The loopback address 127.0.0.1 with IPv4 is now : 1, or all zeros ending in 1 with IPv6. Public IP addresses are referred to as aggregatable global unicast addresses with IPv6. Private IP addresses, so similar to the 192.168, for instance, as defined in RFC 1918 with IPv4, are added a unique local address space, or FC00::/7 with IPv6. Again, these used to be referred to as slight local addresses, but that has since been deprecated. Automatic private IP addressing, or APIPA, with IPv4, you might have noticed if you ever booted up your machine and maybe your DHCP server was dead, you automatically configured yourself with a 169.254 prefix, so at least you can communicate with other devices just on the same link as you. IPv6 has a similar concept, but it's always configured not instead of a global unicast address, but in addition to it, and is actually used for special processes that only need to communicate on a link local basis. Dotted decimal notation is now depicted with IPv6 as : hexadecimal format. And finally, IPv4 started out with the subnet mask idea and then moved on to prefix length, as I mentioned earlier, CIDR notation, but prefix length notation only is inherent with IPv6. So how does a device get an IP address? Well, just like anything, it can be manually configured, but it could also use stateless address autoconfiguration, often referred to as just SLAAC. So in an IPv6 network, the routers send out advertisements, and router advertisements contain a variety of information that the host can use to configure himself. Who his default gateway should be, what his prefix should be, what time to live it should use, or in IPv6 it's referred to as hop count. Also, it can give the host a prefix that it can combine with its MAC address, remember, converting its EUI48 address to an EUI64 for the least significant bits, and then the host can automatically configure itself by just listening for these router advertisements. This is a stateless because the host doesn't actually have to send out a request to get it. It just listens and configures it and makes it very plug and play. So some of the details of SLAAC It's used only by hosts. Hosts listen to routers, but routers must be configured manually. It's used when you're not too concerned about security and such, where your networks inside your organization are trusted, so you're not expecting other routers to connect and give out bogus IP addresses. There is a stateful approach, i.e. DHCP, that I'll talk about on the next slide, and that would give you a higher level of control, but you would still use the router advertisements, and there's a manage bit, whether it's set or not. If it's not set, it's unmanaged, meaning you're using SLAAC, or if it's set, it's the router's indicating to you to use DHCP instead. So what about stateful? So stateful is based on Dynamic Host Configuration Protocol. Of course, it's DHCP v6 now, which is RFC 3315, which has been updated by RFC 4361 and 5494, which is similar to DHCP for IPv4. It could also provide other configuration information, such as WIN servers or other things that you might today get through DHCP, even with IPv4. And again, I mentioned in the router advertisements, there's a managed address configuration flag that will be set to indicate to the device, to the host, to use a DHCP server instead of the SLAAC method, which I described. There's also some options for DHCP v6 from RFC 3633, which describes a scheme called DHCP PD, prefix delegation, and basically adds a few new options. So in a hierarchical type manner, you would have at your site, your main router that connects to your ISP would be referred to as your requesting router, and so it can use DHCP, in fact the PD prefix delegation options, to request from a delegating router at the ISP for an entire prefix range to use. And on the other hand, on the intranet side, it would just use standard DHCP v6 for its own IPv6 client. So it's just a way for your organization's router, in this case the requesting router, to get a prefix from the ISP and then use that prefix to distribute on specific IP addresses to its own clients within. Thank you for taking the time for viewing this topic of the Demystifying IPv6 course on IPv6 Addressing Part 2.